Okay, so let me start. So the first thing that we would do today is a review of a linear regression. Just to make sure that we understand how it works, and then look at some intuition of linear regression and some associated issues and tools that are available for us in linear regression and more generally for all machine learning algorithms. Okay, so the first thing, what was the setup of linear regression? You have certain data. It's a single variable, a single dimensional data. X is a single dimensional, Y is a single dimension. We are interested in finding the relation between Y and X. We say that let's assume that our hypothesis function is, we did polynomial regression. So our hypothesis function is of the form of this. And you can have m number of bases. Again, I should put parentheses because in our notation, power was represented by parentheses, okay? And in order to find these right weights, we constructed a loss function where our loss function was y minus hypothesis of x for all data points I equal to 1 to n. And then we minimize this to find some value of the weights, W0 to Wn. And we saw that it's much more easy, much more convenient to handle this in a vector form. So what we say is that, okay, we will set the problem in a vector form. And the vector form for the problem is this. You just stack these values for the variable x in a big matrix, and this becomes 1 x n xn square and xn program, and you have the weights w0, w1 up till wn. Okay, plus some error terms e0, e1 up till en. And in order to minimize the norm of these error terms, what we say is that we can write the loss function as y vector minus aw, where this is y, this is a, this is w, and this is e. All these are vectors and matrices. Okay, and we found the minima. This is a convex function, so a stationary point is a minima. And we found that the minima is the vector W star is A transpose A inverse A transpose Y, where W star is the minima. Okay, we derived it, we coded it, and it works reasonably well. Now, let's look at some intuition. Why should this work? Why should we be able to find certain weights which combine different polynomial powers of x and give you any y, any arbitrary y? Why does it work? So let's look at some intuition. Okay. So if I say that, let's say I have a point y in R3. So I have a point in a three-dimensional space. It can be any point. And I ask you, I want to write this y in terms of some vectors in 3D. Okay, I want some numbers of vectors. So I'll call them x sub I. So the first one would be x sub 0. This would be x sub 1. This would be x sub 2. Okay, and so on. I need some vectors, and I want some combination of these vectors. I'll call them W1, W0, W1, and W2, such that this combination of these vectors gives me Y. Okay, I have some conditions on these vectors, and the conditions on these vectors is that these vectors are independent of each other, or you can say that they are not a linear combination of each other. Okay, so essentially what I'm saying is that this matrix X is full rank. X is full rank. Do we know what's the rank of a matrix? What does rank mean? Is everyone familiar with it? If not, just please say no, and we will look into it. Okay.
Yes.
Perfect. Okay, thank you very much. So if X is full rank, how many columns of X do I need such that I can write any Y with appropriate W0, W1, W2? Okay, dimensions of Y. Okay, Y is, I've said that Y is in R3. Y is a three-dimensional point. So then 3, okay. So that's exactly the intuition of it. If you want to write any independent Y in terms of the column space of X, where X is a full rank matrix, then you just need 3 columns to write Y. Okay, and you can see why this should work. This would be Y is, like I said, is 3 by 1. X, because X, this X column span is also in R3. So X would be 3 by 3, because each X has 3 elements and you took 3 of them. And I'm saying that it's full rank. And then this is some unknown W1, W0, W1, W2. And we can find this. We know that this would be A inverse Y would be W. And we know that we can find it because inverse of A is possible, because A is full rank. Okay, does it make sense to everyone? So that's basically the intuition. The intuition is that if you have n number of points in n-dimensional space, each point is one-dimensional, then you can find n bases in that particular space, and that would give you, you should be able to fit any data with these bases. Okay. So essentially, if you have, all we need is for these bases to be independent as in they are not linear combination of each other, and we should be able to fit the data with these bases using some weights of them. Okay? So just this condition that they are not a linear combination of each other. This A matrix is full rank. Okay. Now, the polynomial bases that we were looking into were x power 0, x power 1, x power 2, x power 3, and so on, right? X power n. Okay. And sometimes we saw that it couldn't fit the data very well. Can somebody say can somebody tell me what was the reason for it? Why couldn't it it fit the data very well? The polynomial basis. Like for example, in the cosine, we had to like tune the data a little bit to get a good fit. Does somebody want to make a guess as to what might be a possible reason that when we did polynomial regression, for some examples, we didn't get very good answers, even when we were making the number of bases equal to the number of points? Uh, that's uh, that's not precisely true. Sine isn't a polynomial, but the data that we are looking into is not exactly sine. It's a sampling of sine, right? You have certain points. If you have n points and you have n independent bases, it doesn't matter where the data come from. You should be able to capture it. That's we just saw that y can be anything. If these are full rank, then it should work. But why didn't it work in the case of polynomial then? Because this rank often will not be full rank, or will not be like very well conditioned. Like uh, a lot of the projection of a particular vector might be on other variables. So of course, polynomial bases are, if you take it from negative infinity to positive infinity, they are indeed uh, independent of each other. They are not a linear combination of each other. But we are not taking them from negative infinity to positive infinity. Our x is generally like between 0 and 1 or something like that, right? Sampled with some frequency. Okay? And in this range, these might have some, uh, um, one of these might be like a linear combination of some others. And because of that, the rank might not be full, or it might not be very well-conditioned matrix. By well-conditioned matrix, I mean that the inverse might not be very easy to calculate. Okay? So if, for example, some of the eigenvalues of a matrix are very large and some other are very small, then the matrix is ill-conditioned. It's an optimization concept, but what you need to know is that the matrix is not easy to invert. So if a matrix is not easy to invert, then it's a problem. And why is a matrix not easy to invert? Because one of the column is very close to being a linear combination of the other column. And because of that, the determinant is not exactly zero, but it's quite close to zero. And when the determinant is close to zero, the inverse becomes, the values in the inverse might become very large, which are not, which we at times might not be able to handle inside the variable size that is available in a computer. And because of that, you get these issues. So this is one of the issues, which is this is not full rank, and as a result, A transpose A inverse is not easy to calculate. So that's one of the reasons why we had these issues yesterday. Okay, a couple of other side points. We chose these bases. We said that okay, our hypothesis function is W0 plus W1 of x plus W2 of square and so on. But do we have to choose this hypothesis function? We saw that all we need is these bases to be independent. We can choose any bases as long as they are linearly independent of each other. We should be good to go. So what else can we use here instead of these x? What can we use? What could be a good base? Any ideas? Fourier series, okay, sine cosine bases are a good option. Okay, and how would that look? So you can have, let me call this xp for polynomial. You can have s cosine basis x. This would be w0 plus w1. In fact, okay, w1 cos of pi x by x plus w2 cos of 2 pi x by x and wm cos of m by x by x. Okay, so these are Fourier bases. Let me just tell you what these are. So let's say this is your x is between 0 and x. Let's call this x max because I use x for something else. the maximum value of x that's possible, and x is between 0 and x max. So this one, if you plot this, the first base, well, the first base is DC, but the second base. So this would be like this. It's a cosine, so it should be 1. It should be like this. Okay. Then when you plot the second one, it should be like this. My drawing might not be very neat, but this is how these bases look. I'll try to get a plot in code, but what I'm trying to suggest is that these are the good thing with these cosine bases are that they are completely independent of each other. They are orthonormal. By orthonormal, I mean that they're dot product with every other. So the dot product of this with any of these others is 0. And with itself is 1. Well, it's not 1. It's some factor of 1, like n or m, something like that. Okay. So they are completely orthogonal to each other. So these are actually some good bases. We will see what these bases are. So rather than having polynomial bases, where we had a, which was polynomial basis, which is x, x power 1, x power 2, and so on, we would have this. I'll call it a cosine. So this would be cos of 0x by some factor x max. And there is a pi here as well. We would have cos of 1 pi x by x max, cos of 2 pi x by x max, and so on. M number of bases. Okay. Again, you can have any basis here, any function of x. So in general, you can have something like this. You can have f0 of x, f1 of x, f2 of x, and up till fm of x. As long as these f's are linearly independent of each other, we are good to go. Okay. The simplest case, of course, is just take the polynomial. f0x is x power 0, f1x is x power 1, f2x is x power 2, and so on. That's the simplest option. You can go for the cosine one, where f0 is cos of 0 pi x divided by x max, f1 is cos of 1 pi x divided by x max, and so on. Okay. Is this clear so far? That we can take any bases in regression. We do not have to take linear bases in regression. Can I get a few yeses in the chat so that we can move forward? Okay. Okay. By the way, if anything is not clear, please ask questions, because this is just meant to be a discussion. I want to explain these things to you. If, for example, something doesn't make sense, just simply say, oh, I don't understand it. You don't need to write it in the chat to everyone. Just send me a direct message. Say that, okay, teacher, I don't understand this, or Naeem, please explain it, and I will explain it for you guys. Okay? Okay. Let's look at another type of basis, another basis that we would actually look in some examples for today. So these are called Gaussian bases. Gaussian bases. So can somebody tell me how would we write the expression for a normal distribution? What is the expression for a normal distribution? From probability or Gaussian distribution? Okay. Are you guys familiar with Gaussian distribution, by the way?
Yes.
Okay. So Gaussian distribution around mean mu and with standard deviation sigma would be 1 divided by under root 2 pi sigma exponent x minus mu whole square divided by 2 sigma square. If I'm not wrong, I think this is how it is, right? Okay. So
Yes.
yes. So basically what we can do is we can see that this depends on two variables, mu and sigma. This is the mean and this is the standard deviation. So basically, if let's say we take the mu 0, you would have the Gaussian distribution looks like this. So this may be, let's say this sigma equal to 1. If you make sigma equal to 2, take another. If you make sigma equal to 2, this might look something like this. Again, this is just schematic, just to explain what the sigma does. It might not be exact, but roughly this is what it does. If you make sigma equal to 3, it might become something like this. It's always decreasing, by the way, so don't get confused by my drawing. It's always decreasing for x greater than mu and always increasing for x less than mu. Okay, so that's what sigma does. That's the control of sigma. What does mu do? What happens when you change the mu? Mu just shifts the function. So this is let's say, sorry, this is mu equal to 0. If you let's say make mu equal to 1, this would just shift this to 1. Like this. Exactly same function, just shift it. There should be, of course, there should be a minus in the exponent, yes. Because if there isn't any minus in the exponent, it will just go up, increase. Okay, so that's how Gaussian distribution Gaussian function look. So basically what we can do is, let me just clean this up, that's right. How we can use Gaussian basis. So what we can do is we can say that, okay, let's say that we have x in our particular task is from 0 to, let's say some x max. Let's say I want to choose 10 number of bases. So what I do is I say, okay, let's linearly divide this space into 10 parts. So let's say this is 1, 2, 3, 4, 5, 6. Let's call it 7. 7. And then let's define one Gaussian at each of these center. You can, of course, change the sigma as well, the standard deviation as well, but we would assume that standard deviation is constant. We are just changing the location of the Gaussian distribution. So the first base would be a Gaussian distribution at this point. So this is my first, this is base 1. Okay. The second base would be a Gaussian distribution at this point. I shouldn't call it a Gaussian distribution, I should call it a Gaussian function maybe. And the third one would be a Gaussian function at this point. So these are my bases now. And so on. So I can use these as my bases as well. Okay. So again, let me just write the A for this. The A matrix for this, let's call it A Gaussian. Would be, I'm going to just drop this constant because it doesn't matter if you have this constant or if you don't have this constant, it doesn't matter. It doesn't depend on mu, and our Gaussian function are dependent on mu only. If I'm just going to drop it in my notation, just write the exponent form. So we would have exponent of minus x minus mu 0 whole square divided by 2 sigma square. This is the first base. Exponent minus x minus mu 1 divided by 2 sigma square. This is the second base. And this would be x minus mu m whole square. This would be the mth base. So you can have Gaussian bases as well. Okay. Everyone is clear about how we can use cosine bases and Gaussian bases? Okay. I need a few more yeses. So sigma is the same for all of them. Yes. In my particular example, I'm assuming sigma to be same for all of them. You can, I think it shouldn't matter. You can change sigmas as well. But for my case, the example that I'll do today, I'll assume sigma to be same for all of them. Okay. Any other questions? Why do you use Gaussian distribution? You don't have to use Gaussian functions. You can use any functions. The thing is, we want to have some basis functions, and this is one basis function, which is nice. What is the benefit of using Gaussian distributed polynomial basis? Well, one thing is that Gaussian bases are spatially limited. So you can see that kth base is active around a certain point. So by looking at these, the weights of these, you can say which base is active around which point, and what is it doing. So we will see this in an overfitting example. I'll explain why it's just better for visualization and explanation, that this is better. I don't know whether we can have like a general form where we can say that this space is better in all cases. I doubt that we would have a case like this, at least not in my knowledge. But for certain visualization purposes, certain explanation purposes, this one is quite better. We would see in one of the examples later today. Okay, any other questions? Okay, perfect, perfect. So let's look at some other associated concepts today. So there is a concept of underfitting and overfitting. This is associated with all machine learning algorithms. Okay, so what is an underfit? Let's say you have a cosine. You have data from a cosine. In fact, let's make it a little noisy. So maybe a few points are a bit noisy. Okay. And the rest of the signal is fine. So let's say that there are some noisy samples. Okay. And let's say we are looking into this polynomial basis. We're trying to say that h of x is equal to w0 plus w1 of x. What do you think we will get? The data is what we have on the screen. What would be the best fit in terms of this hypothesis function? What would we get? Remember that hypothesis function can only give you a line, because that's how you have defined it. Okay, and that's line. And the best fitting line for this data would be something like this, because that would minimize the error. If you have a line like this, it would have small error for this, but much larger error for this part. So this is not the optimal line. The optimal line is something like this. So now my question to you is this a good fit? No, it's not a good fit, right? And why is it not a good fit? Because our function, the hypothesis function that we work with, is not complex enough. Okay, that's what's called an underfit. So that's an underfit problem, where the hypothesis function that you chose is not complex enough and could not capture the underlying function well. Okay, so let's look at an overfit and see what an overfit is. I'm just going to, I think I lost some of the points. Okay. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points. Let's say that I take my hypothesis function h of x, w0 plus w1x plus w12 x power 12. Okay. What did I do? I think I undid my drawing. Anyway, let me just redraw it quickly. Point here as well. 2, 3, 4, 5, 6, 7. It's 9, 10, and 11. Let's call it 11. So this is overfitting. And let's say that my hypothesis function is W0 plus W1x, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, plus W10 x power 10. And for the time being, let's assume that all of the bases are completely independent of each other. The polynomial bases are completely independent of each other. How would the fit look? How would my solution look? So you have, remember, you have 1, 2, 3, 4, 5, 11 points, and you have 11 independent W's. You have 11 bases, and all these bases are independent of each other, we are assuming. So how would my solution look? The h of x that I get, the optimum h of x, how would it look? So let me call it h star. H star is the best hypothesis function. How would that look? Remember, we saw that if you have n points, n data points, and you take n independent bases, you can learn them exactly, right? That's what we discussed in the earlier part of the lecture today. Now here you have 11 points and you have 11 bases, and I'm telling you that these bases are completely independent of each other. So what do we expect? How do we expect h of x to look? It will fit all points. It will fit all points exactly, right? So you would have something like this. It has to be smooth because our bases are smooth, but it would go to through all the points. And now, do you think this is a good fit? Of course, it's a good fit to data. Is it a good fit to the underlying function? No, it's not a good fit to underlying function because the underlying function is a cosine. Okay, now that's what we called an overfit. Okay, and there are multiple ways to solve the problem of overfitting. Okay, they are broadly put under the umbrella of a term called regularization. Okay, so let's look at regularization. One of the things which we observe, I don't know whether there is like a mathematical proof for it in any books, but generally I did not see it in like typical machine learning books like Bishop. It's just given as a point that if you do a case like this, you would see that the weights which are well, you can say that some of the weights which are correlated with each other somehow start becoming very large. When you have this case where you go through all these, their magnitude becomes very large. They become larger and larger and larger. And this large magnitude is primarily mostly spent toward this overfitting. It does not learn the underlying function. So what people do is we say, okay, what if we start penalizing this weight? If the weight is used toward overfitting, why don't we penalize this weight? So what we do is, what was our original cost function? This was y minus AW transpose y minus AW. People say that let's do this, add a term to it where you do from I equal to 0 to m. Remember, m is the number of bases that you have, w of I whole square. So you take the square of all the weight components. Okay, you take the square of W0, W1, W2 up till Wn. Okay, and what is this? We saw this term yesterday for where we had summation I equal to 0 to n ei, and we wrote it in some nice way. We said that, okay, this you can write it well. How did we write this yesterday? In yesterday's lecture, we said that if you have, sorry, EI square. If you have the square of each component of a vector, what does it represent? The sum of the square of each component of a vector. What is it? Yeah, it's a dot product of the E with itself. And you can write it as E transpose E, which is a vector. So you can do the same thing here, right? You can write it W transpose W. Okay. So now our cost function becomes Y minus A W transpose Y minus A W plus W transpose W. Okay. And if we find its gradient with respect to the weight vector W, this part would remain the same. This would be minus 2 A transpose Y minus AW plus 2 times W. Okay, this is exactly the same as what we extracted yesterday. This is the derivative of this. Is it clear? So the derivative of this is here. This we had extracted yesterday. Okay, so let's set it equal to 0 and let's see what we get. So we get, we can drop the 2 from everywhere because we can divide both sides by 2. So you get minus A transpose Y plus A transpose AW plus W is equal to 0. Let's further simplify it. This becomes A transpose AW plus W is equal to A transpose Y. And if we want to collect W from here, we can write it as A transpose A plus identity times W. Remember, these are vectors and matrices. So the equivalent of 1 would be an identity is equal to A transpose Y. And then W star, which is the best solution to it, this would become A transpose A plus identity inverse A transpose Y. So without regularization, by the way, this is called L2 regularization because we have square norm here. You have the square norm here, so it's called L2 regularization. So without L2 regularization, we had W star is equal to A transpose A inverse A transpose Y. But once we do the L2 regularization, we get an identity added with A transpose A. Okay. Now what you can do is, depending on different tasks, you might want to weight this term differently. You might want to put some lambda here. For some application, you might want to penalize the weights quite a lot. For some other application, you might not want to penalize the weight quite a lot. So you generally weight it. You weight it by a term lambda. So if there is a term lambda here, lambda is a constant. It just simply carries on everywhere throughout this calculation. And you would have here a lambda identity. Lambda gives you the control of how much normalization you want, whether you want the weights to be really penalized or you want the weights not to be penalized too much. So you can control this by lambda. And we would see the effect of lambda today. Okay. Intuitively, what does this do? What happens when you add lambda to the diagonal of a square matrix? It adds lambda to all the eigenvalues of that square matrix. So all the eigenvalues would be increased by a value lambda. And if all the eigenvalues are increased by a value lambda, it basically makes uh, um, the, the inverse easy to calculate. How does it make inverse easy to calculate? Well, if you have a diagonal matrix added to a matrix, then you can be sure that the matrix is full rank. It would be full rank because you have added, at least this is full rank. Unless these two are additive inverse of each other, the solution of them would also be full rank. Okay? Unless A transpose A somehow cancels out this lambda identity, this would be full rank, and as a result, its inverse would be easy to calculate. So that's the intuition of why it helps. Okay, so again, L2 regularization is not the only regularization we have. We can look at other regularization as well. There is another regularization which is called L1 regularization. There are other names for it as well. So this is called lasso, and this is called regularization. So we are doing L2. This is called ridge regularization. So these are different domains use different name. I think this ridge and lasso is probably from statistics, these names. Yeah. Okay, so what is lasso regularization? So lasso regularization is exactly the same concept. So what you say is that the cost function is y minus a w transpose y minus a w plus the absolute value of, so you just add the absolute value of all the components of w to the loss function. Okay. You can take the derivative in a similar manner. So this would become minus 2a transpose y minus aw plus the sign of the vector w, the sign function, because it's either plus 1 or minus 1 depending on where you are. We cannot find a closed form solution for this because this is not like a well-defined function. It's a discontinuous function. But you can use iterative techniques to solve it, and we would see them in day 6, how to solve this. But this is just another way of looking into it. There are certain advantages of lasso over L2 regularization, L1 regularization over L2 regularization. So let's have a look at this. So let's say you have two waves, W0 and W1. Okay, so this is W0, this is W1. So what would be W0 square plus W1 square equal to, let's say, C? How would this look? It's a circle, yes. So you would have, as you increase C, you would get these different concentric circles. Okay? So that's how L2 norms looks. It's like circles. What would be this? What would be W0 this plus W1 this equal to C? How would this look? The absolute value of W0 plus W1 equal to C. Let's look at it in the first quadrant. The first quadrant where W0 and W1 are positive. So this would be W0 plus W1 equal to C. What is this? Now this is a line, yes. It would be something like this. You can do it for all other 4 quadrants. It would turn out to be like a diamond. And as you increase the value of C, this diamond would become larger and larger. And so on. Okay? So 2 things. One is L2 regularization looks like a circle in 2D. In higher dimension, it could be a sphere. And L1 regularization looks like a diamond, a two-dimensional diamond. In high dimensional space, it would be an n-dimensional diamond. Okay. Now, what is our cost function? Our cost function is y minus AW transpose y minus AW plus regularization. Okay. These are quadratic functions. So these are squares, right? Because they are square functions. It's like equivalent to squaring all the terms. We saw this loss function, it looks like this, right? So it means that they are circles. So different different loss, different value of, so basically I'm trying to see this thing, let's call it J1. So if we put J1 equal to C, again, you would get some circles like this in space. So let me do some cleaning up so that I can show them. Okay, so J1, of course, it's not centered around origin. It can be somewhere in the space of your data. So it would, let me draw it in blue. So it would be like this. And the intersection of this with your this is likely to be somewhere like here. So the intersection is basically the sum. It's this plus this. It would be somewhere here, right? The intersection with diamond, however, is more likely to be at one of these corners. That's because of the shape of the diamond. So it's more likely to be at one of these corners. And that's one of the main advantages of using lasso. So what is the good thing about these corners? Can somebody tell me what is the main property of these corners? What is good about these corners? Well, the main property of these corners is that some of the weights are zeros at these corners. You can see that W1 is 0 here, W0 is 0 here, W1 is 0 here, W0 is 0 here. Right? This is a good property because this is called sparsity. You don't need to store all the weights. You know that some of the weights are zeros. So you can save a lot of memory. So the advantage of L1 norm is that it's sparse. L2 norm, on the other hand, is not sparse. So this point, neither W1 is 0 nor W2 is 0. Some of them can be small, but they're not 0. So that's the advantage of L1 norm over L2 norm, sparsity. Okay, is it clear? Okay, perfect. So let's try to implement some of these things in code. Just give me 1 second. I'll get a glass of water and I'll be back with you guys. Okay, so again, you define an instance of a linear regression model. You give it the training data and the training label, and you ask it to fit it, to learn something from it. Then you generate your test data, which is just axes. You don't need to have label for it. You generate the basis for it, which is x power 0, x power 1. You give this data to the model and you ask it to calculate predict the y label for it. And then you just plot your data. Your original data, training data is in blue, and your learned data, which is fit to this model, is in orange. And you can see that it fits the model quite well. Is it clear so far? Does everybody understand how to use model? Okay. Okay, I want to see some more yeses because we just have 2. Excellent, excellent, excellent. So let's do this for cosine basis. Let's write the same thing for cosine basis, and let's see what happens. So let me just copy this line of code, these 2 lines of code, and let's do it in cosine basis. Probably it's better to have a slightly complex function than this. So let me see what else, what other functions do we have? Okay, I think this might be nice. So let's do this. Let's take this as our data for this problem. Okay. Okay, so my data is something of a, it's a sine. And remember, I'm trying to write it in cosine basis, so it's not that straightforward. But let's see what happens. So the first thing I need to do is define some number of bases. Let's say I take 5 number of bases. And like I said, like we did in the notes, the cosine bases are this: cos of x pi times x times k divided by x max, right? And this k goes from, it increases 0, 1, 2, 3, 4, 5, depending on what you want, okay? So what we need is this x max. Since x is fine, it's always positive. So I can just say that x max is np dot max of x. That should be fine. What else do I need? That should pretty much do it. Now I need to find the bases. So I'll do bases underscore train. Again, I'll use broadcasting. So basis underscore train is np dot cosine of, let me do one other thing. So let me import math. Math library has math.py, which is the value of pi. So I'll say that pi is equal to math.py. So pi times x. Can we choose the number of bases arbitrarily? NumPy also has pi. Okay, I did not know that. If NumPy has pi, then I can just use this np.py. Yes, the number of bases, you can choose it arbitrarily, but you have to choose it smartly. It's not a completely independent thing. It depends on the type of data that you have. If you choose it too low, you will have an underfit. If you choose it too high, you would have an overfit. So if you're choosing a higher number of bases, it's good to have some regularization as well. So my suggestion would be always go for higher number of bases with regularization, and that would probably work. Of course, not exuberantly high, not go out of the way to make it very high, but a large number of bases with some regularization would always be good. Okay, so now let's see what do we need. So we would have pi times x times k. I have to first define what k is. So k, in the previous case, where is my basis? Okay, it's here. So k would be np dot a range num underscore basis. Again, I'll use +1 because I'll not count 0. I'll just count from 0 to m. So that's why I add a 1 here. So let's give it the right shape. So this should be np.axis for broadcasting. And k should be np.new axis. This. That should pretty much do it. I think it should be fine. Let's just look at the shape. Shape. Of 50 times x, it seems fine. So let's do this. Let's say model.fit. And this is train and y. And again, I will generate my x in this range. and y fit would be model.predict. Again, I have to create basis for it. That should work. Do the plot. A question for you guys. When I'm plotting x and y, I'm always giving it this dot parameter. Can somebody tell me why this is the case? Why don't I want to plot the line for x and y? Okay. So how many bases are there? 5, maybe 9. Okay, I think I might be making some mistake. np.cos by xk. Oh, yes. What is the mistake? I haven't normalized by x max. In fact, in this case, I know that x max is 10, so I can just directly write 10. Okay, so that seems very good. I'm actually quite satisfied with this. Does everyone see what happened? So it's a cosine basis fit. So let's do this. Let's just plot these bases and see. What do we get? So we say for I in range basis dot shape 1. Plot, and this is so these are the bases. You can see that it's too large. Let's make it 5 so that we can see them well. You can see these are the bases. This is the 0th base, or the DC component, sorry. Then it's k equal to 1. Green is k equal to 2. The purple, I think, is k equal to, red is k equal to 3. Sorry, orange is k equal to 1. Red is k equal to 2. Purple is k equal to 3. I might be missing a few, so I'm sorry. Orange is k equal to 1. Green is k equal to 2. Red is k equal to 3. Purple is k equal to 4, and brown is k equal to 5. So these are different number of bases. Okay, and like I said, the good thing for cosine bases is that they are orthogonal. So let's do this. Let's see if they are indeed orthogonal or not. For j in range basis dot shape 1. So what is it? NP dot should give me the dot product of these two, right? Comma j comma np. I will correct it. Yes, of course. So let's run it. Okay. So let's see. This value would be a positive number, a large positive number when I and j are equal, and it would be close to 0 otherwise, or very close to 0 otherwise. Okay. So for example, this 0, 0, it's 1000, and then it's either very small or like, well, compared to 10 to power 3, it's very small. So this is 1, but it's 1000 times smaller. Only when I and j are equal would this number be large. Other than that, this number would be very small. which means that A transpose A would be a diagonal type of matrix. Does everyone follow what I'm trying to say here? So you can see that it's when I and j are equal, the dot product is high. For every other combination of I, the dot product is very low, which is a good thing, which means that this is A transpose A would have high numbers on the high positive numbers on the diagonal and very small number everywhere else, which means that its inverse would be easily calculated. Okay. So let's do the Gaussian basis one as well. And after that, I'll give you guys some time to practice these exercises, and then we would try to do a nice example in 2D for images. So let's copy the data. By the way, if there are any questions, please feel free to ask. So what do I need? So what did we decide to do? For the Gaussian basis, we decide to split the range, the maximum and minimum value of x, and divide it between n number of bases, right? So what I need to do is I need to find x min. X min is np dot min of x, and x max is np dot max of x. So centers would be np dot plane space x min, x max, and basis. So this gives me the center, the center for all the Gaussian bases that I want to calculate. One other thing that we want to do is we don't want to have the sigma as a constant number. We want the sigmas to be related to the centers that we have. So basically, let's say that if the distance between my centers is 1, then maybe I would want my sigma to be 2, something like that. So it's better to directly relate sigma to the difference between the distance between two consecutive centers. So let's say I call it, I think, let's call it width factor. And I think probably the notes that you have with the width factor is chosen as 2. So I'll call it sigma. Sigma would be width factor times centers 1 minus center 0. This is the difference between two centers. And now I think we are good to go. We have all the centers. We have the sigma. We just need to calculate the bases. So again, I would use the same strategy. It would be np.x, x minus centers divided by, of course, this is whole square, divided by 2 times sigma whole square. Now let's do the broadcasting. So for broadcasting, this has to be np dot mu x's, and this has to be np dot mu x's. This, I think this should work. Let's look. Let's see, everything is good. Okay, seems to be fine. Let's try to fit the model. Again, I should call it basis.train. I don't need this anymore. Model.fit and basis underscore train and y. Let's take the test data. Here. Okay, so this should be fine. Let's run it and let's see what goes. Again, also a very good fit. Let's plot the bases. Okay, remove the code. So for I in range of bases dot shape 1. Uh, and you can see that these are Gaussians at different points. Just the centers are moving. Again, the data it's a very good fit. Okay, is it clear so far what I did? Yeah. Excellent. Let's have a look at some overfitting and underfitting. So I'm going to copy this. Underfitting is easy to see. Let me just give it 1. Yeah, probably 2. I don't know what the error is, but I don't want to debug it now, so I'll just avoid it. So this is an underfit. Okay, let's give it something large, like maybe 30. Now you see this is an overfit. You see that it's this thing. It's not a cosine, right? We don't expect this in cosine. So it indeed has these weird jumps. Even some jumps here as well. These ripples. We want to remove it. Okay, so let's try to remove them with ridge regression. Okay, so let me copy this whole thing. Put it here. Let's call this regularization. So I'm going to train, what should I do? Should we just do the ridge regression and look at it, or do you want to look at the ridge regression and linear regression in the same figure? Up to you guys. Just tell me which one should we do and we will do it. I can just do the ridge regression and show you the output of ridge regression, or we can do the ridge regression and linear regression and show them side by side, or in a single plot. Okay, so let's import this and ridge, probably lasso as well. Maybe we use it somewhere else. Okay, so I have one model here, and then I'll call it model underscore regularized, and let's call it ridge. It takes in a parameter. I just need to look at its representation. Okay, where is model define? Okay, so it takes in this parameter, which tells it how much regularization to use. Of course, you would have to find it the optimal regularization for each case. I did not want to go through like checking all of these, so I just copied it from there. Again, nothing too fancy. The same thing, like you did model fit here, you would do model underscore regularization fit. And like you did y fit, you would do yfit underscore regularized, and we can plot this on top of this as well. Okay, let's run it. Let's see what happens. Okay, this has to be 30. Okay, this is not model. This is model underscore regularized. Okay, so now let me try to set the while limit such that you can see it a little better. Top, bottom, and top. So okay. So since it's a cosine, we probably need something like 1.1 and 1.1. Let's run it. Okay, so now you can see that the green one is the unregularized one, and it has these ripples, and the red one is the regularized one, and you can see that it's very well adjusted. Yes, thank you. So you can see that that's the advantage of regularization. It kind of avoids this following up this going after these unnecessary noise in the data. You just concern yourself with the actual signal. You don't follow the unnecessary noise. Is it clear? Does everyone understand what the regularization did? Okay, let's do L1 regularization as well. I'll do it the same way. So probably this is not a nice notation. I should call it L2. Hopefully it calls this parameter alpha as well, so I don't have to change anything. If there is an error, I will have a look at documentation and try to fix it. Okay, let's run it. Okay, so probably alpha for L1 is high. Let's make it small. Okay, so pretty much the same thing. Now let's look at the weights. One of the things that we said is that the weights for L1 regularization are 0, they're sparse, and L2 regularization, they're not sparse. So let's do this, and let's see if this is indeed the case. So what is it called? Model.L2. I think this is called coefficients. And similarly, PLT. plot it's plotted. Let's see. So this is indeed the case. You can see that for L1 regularization, the weights are, lots of the weights are zeros, which is good, which means that the matrix, the vector is sparse. You need less memory to store it. So L2 regularization, well, some of the weights are high, some of them are small, but none of them are specifically zero. Whereas for L1 regularization, most of them are zeros. Does it make sense to everyone? Excellent. One other thing that I want to show is probably the norm of the, yes, we want to see this. So plt.plot and centers model. Okay, can somebody explain to me what's going on in here? So I'm plotting the coefficient, the size of the weight of each base corresponding to the location of that base. So again, let me do something. Okay, so well, it's not very easy to see, but anyway, basically here I'm showing the bases where each base starts, and here I'm showing the magnitude of each of the base. In fact, it might be better to just look at the signal here. And probably this might be better. Okay, you guys didn't answer me. Why do I plot, when I plot X and Y, I plot it with a dot? But I don't plot the fit data, X fit, I don't plot it with the dot. I plot it with a line. Well, because the training data is generated randomly. So it's generated randomly. So there is no guarantee that X is increasing. Whereas the test data is generated by lens space. So X is always increasing. So it's fine if it's connected by line. But if it's random, then it's connected by line, you would see this zigzag pattern. So that's why I plotted with dot. So basically what happens is what these represent is the weight of the corresponding base. So you can see that at this part, when the signal is fine, the weights are fine. But here where there is noise, the bases jump very high. Again, here where has noise, the bases magnitude jump very high. And they cancel each other. Like if this is very high minus, this is very high plus. And since they are close to each other, the closer two Gaussian bases are to each other, the more correlated they are because the more overlap they have. So since they have overlap, their magnitude increases and their overlap cancel each other. Okay, and that's why we put this regularization, because we don't want these jumps, large ripple of the weights, where one large weight cancels the other large weight. Okay,
in its neighborhood where there is spatial correlation. So that's why we have this L2 regularization to kill this weight increase because of correlation between different bases. Does it make sense to everyone? Okay, perfect. So here I'm going to stop the lecture part of it. Try to go through the notebook that I've shared on the website, and all the codes are there. It would be better if you guys do what I did, which was just try to write the code yourself for sine basis and Gaussian basis. But if, for example, it's a bit challenging, you can just look at the code and try to do it. Again, the code does it in a slightly complicated way. So the code that I wrote, it kind of writes it in a much simplified way. So try to write this, like replicate this. I will share this notebook with you guys anyway, but I don't want to share it with you right now. I want you guys to give it a try. So use the same data as is in the notebook. Let me just go to the website and you guys. Okay, so this notebook. Yeah, so this is the notebook. This is from this Python data science handbook. A nice book and some very nice exercises. So copy the data and then just do exactly what I did. They have everything which I have done has been done in this notebook as well, but it might not be very straightforward because they use some complex tools of sklearn, which I have avoided. I've just kept it very simple and rewrote the code. In any case, I'll share my codes, but try to reproduce them. You have around it's 10:30, so we will be meeting back at, when do we usually take the break? At 11, right? Yes, the break is at 11. So you have 30 minutes. We will be meet back at 11:30. I would resume my lecture at 11:30. I'll give you an example of linear regression in 2D, which is a nice example, a practical example actually. And then after that, you would have around 1 hour to re-practice these things and see how you guys absorb it. Okay. If there are any questions, I'm available in the chat. Please feel free to ask them. And see you guys back at 11:30. Okay. Thank you. Okay, guys, welcome back. Is everyone with me? Can you put a simple yes in the chat so that we know that people are back? Excellent. Okay, so let's look at another application of linear regression that I really like. So we'll call it linear regression in high dimension, linear regression in high dimensions. Okay, particularly 2D, or the particular example that we are looking is linear regression for images. Okay, so let me just motivate it a little bit as to what I mean by this. Okay, so basically what we did is we saw that, okay, if you have a vector y and you have certain bases, f0 up till fm of x, then you can write y as some combination of these bases. Okay. Now this can be used in certain applications, one application being image compression.
So what can we do? So let's say that you have an image which has a size of it's 1,000 by 1,000 pixel image. Okay. And let's say I know certain number of bases. Let's call this m equal to 200, such that, sorry, 2000 maybe, such that when I construct the image with these 2000 bases, so I'll call it h star of x from these 2000 bases, the difference between y and hx is very small. So this is, let's say, quite small. Then I don't need these 1000 by 1000 pixel to store the image. I can just store it with these 2000 weights, right? I can just store these 2000 weights, and then whenever I need the image, I can generate these bases, use this 2000 weights to produce the image. Does it make sense to everyone? So rather than storing large images, you can store the representation of the images in this particular basis, any basis that might be of interest to us. Okay, we will actually do it in code as to how we actually, what are these bases, how do we calculate them, and how do we store them. So this is used in JPEG images. JPEG images, these use DCT transform, these discrete cosine transform, to compress images. Although they are not a direct application of linear regression, they are a type of linear regression. We would find them out with linear regression. Okay? So we will calculate the DCT transforms. So what are DCT transforms? We already saw the cosine transforms. So when we have 1D data, y was cosine of pi k x by x max, and summation k equal to 0 to m, right? This is in 1D, this is the data. So in 2D, if y is in 2D, so I'll call it y of u and v to represent that it's a 2D data. This becomes, I'll call it I and j rather than k. So this would be I equal to 0 to m cos of pi I x u divided by x u max times cosine of pi j x v divided by x v max. Okay, and of course there are optimum weights for it, wk, and here it would be w of I and j. So basically we can find these wijs, store these wijs instead of storing the image, and then whenever we need the image, just reproduce the image from these wij. So let's do it in the code. Let's see how we actually do it, and see if it's useful. So let me share my screen. Can you guys see my screen? Okay. So let's see what is the image that I'm working with today. So I've just generated a simple image, which is 1 in the foreground, 0 in the background. And I need to, let me write the expression, what we need to do. We need to construct the bases where the bases are
cos of y times I times x, x of u, okay, and times cos of y times j times x of v. Okay, so let me call them u and v. Okay, so x of u I will call this. So x of u, I'll call it u, and x of v, I'll call it v. Okay, so first, of course, this is normalized. This is divided by x max and x max. So I'll call it u and v. So basically this thing, x divided by x max, this goes from 0 and 1. So we can make the problem a bit easy to tackle. We can do something like rows, okay, let's call it n rows and n calls. This is the number of rows and columns in the image, im.shape. Now we have to produce x by x max, which is from 0 and 1. And of course, it has number of rows and number of columns. So I can call it rows is equal to np dot linear space. So it's from 0 to 1, and it has n rows. And similarly, you have columns, np dot space between 0 and 1, and calls. And now since these are vectors, right? So let me do this. So this is just a vector, but image is 2D, right? It's not a vector. This vector is repeated equal to the number of columns, and the column vector is repeated equal to the number of rows. So to get this, we use something which is called mesh grid. So u and v is np dot mesh grid, rows and columns. And now if I look at this, would be equal to the size of the image. Okay, 28 times 28. So it takes in the row and repeat it n times, equal to the number of column times. It takes the column repeated equal to the number of row times. Does it make sense to everyone? What I did here? Okay, I need a couple of more yeses. Excellent, perfect. So next let's define some number of bases. So let's say I take 10 number of bases. Now I have to write this cos of pi x divided by x max. So I have this quantity and I have this quantity. I have to define I and j. So I would be np dot a range num underscore bases. Similarly, j would be np dot a range number of bases. Okay. So now I have u, v, I, and j, and I need to broadcast such that for each combination of I, j, u, and v, I have a corresponding base, right? So basically, if I change I or if I change j, I get a different base. So let me discuss a broadcasting strategy with you and see what you think. So, sorry. So right now, the shape of U is rows n rows time n columns. This is shape of U and V. And of course, I and J are just n bases. Their shape is n bases. Underscore bases. So what should I do such that for each I and each J, I get a combination of U and V inside this cosine? What do you suggest? Of course, we need to insert ones to make them compatible, but how do you want the dimension to look? Do you want it number of rows, the dimension of bases to be number of rows, number of columns, number of I, number of J, or number of I, number of J, number of rows, number of columns? We can do it two ways. So what do you guys suggest? What should we do? Just put an option 1 or 2 in the chat. I know both are equally good, but just, I would leave it to you guys. So I'm looking at the chat. Option 1 or 2. First row calls an ij. Okay, let's do that. So if we do that, then I need something like this. U is equal to U. So this np dot new access and np dot new access, right? Same for V. Okay, and for I and J, we would have something like I is equal to I, np dot new access, np dot new access, comma this, comma np dot new access, and J would be J times np dot times new access, np dot new access, np dot access, and this. Okay, so basically x and y are in the first two dimensions. This represent the rows of image, this represent the columns of image. The third index represent the x component of cosine, and the fourth component represent the y component of cosine. Does it make sense to everyone? Does everybody understand this broadcasting scheme? Okay, so let's get the basis. Basis would be np dot cosine pi is equal to np dot pi. So np dot cosine pi times u times I times np dot cos pi times v times j. I think that should do. So let's look at basis dot shape. Okay, so that's exactly what we expect. 28 times 28 times 10 times 10. Now, things can be done in 2D, but it's much more convenient to vectorize the image. So rather than working with two-dimensional data, let's put all the columns of the image in one long vector. So what I can do is, I can do something like this. I can say basis is equal to np dot reshape basis, comma, basis dot shape 0 times basis shape 1 shape 2 basis dot Basically, I'm making it a square matrix where each column is stacked version of the image, one base, and the bases are along the columns. So let's do it and let's have a look. Shape is not defined. Of course, this is street shape. Okay, that's exactly what we expect. Now let's do the same thing for image. So I'll call it IM. I want to stack the image as well. So IM. Let's call it stack, and this is np dot reshape image to stack shape 0 times image dot shape 1 times 1. So I've converted the image into a column vector as well. This. Okay, so now everything seems fine. Now the weights would be just np dot linear algorithm inverse. A in our case, I call it basis, basis dot t product with basis, and then its product with basis t and stat. So this gives us the weights, and then I can I call it image underscore DCT would be basis product with W, and let's reshape it into an image size. So np dot reshape DCT image dot shape 0 and 1. So again, converting it back to a square matrix. Let's do some plots. Let's run it and see what happens. Okay, so seems like things are fine. So if I use just 10 bases, the reconstructed image looks like this. Let's increase the number of bases. Let's make it 15. If I use 15 bases, the reconstructed image looks much better. If I use, let's say, 20, it's even better. If I use 28, it should look exactly the same. Should look exactly the same. So that's basically how DCT works. So rather than storing the image, you store these W's. And W's can be much smaller. In this case, we don't get lots of compression because there is a very sharp edge. Generally, in images, the edges are not that sharp, and larger images, you would see that you can get significant compression. So again, the idea is that you find these weights for an image. How do you do that? You just need to construct bases. Bases, by the way, in this case, are independent of the image. They just depend on the shape of the image, the size of the image. You can see that I constructed it with just the number of rows and number of columns. Okay, you can construct these spaces anywhere. You just need to know that the size of the image is, let's say, 1000 by 1000. So you can construct these bases. And once you have these bases and you have these weights, you can reconstruct the image. So rather than storing, let's say, 1000 by 1000 pixel, which is 1 million points, you can store maybe 2000 points and then reconstruct the image with not a lot of error. So that's basically the core idea of discrete cosine transform. So FFTs and DCTs, we study them in signal processing as a separate tool, but they are also a type of linear regression. You are trying to find the optimal weights in certain bases for your signal. Okay. Does it make sense? Is this code clear? I know it's a bit tough, but it's not super tricky. Right? You just need the index of the number of row at each location, the index of the number of column at each position. Could you use sine instead of cos? I'm not sure. Let's try it. There are certain advantages to cosine because cosine is the real part of the complex exponential. But let's see sine and let's see what happens. Yeah, yes. So the thing I think with sine is that you can get some singular values. I think that's why probably we don't use it. So sine is probably not a good idea. It's better to use cosine. Oh, yes, of course. Of course, it's not going to work. So if you, let's see why it won't work. Let's put I equal to 0 and j equal to 0. So you will get np.cos of 0, np.sine of 0. What is cos of 0? This is 1 and this is 1. So you get a constant. But if you have sine of 0 and sine of 0, you will get a 0. And you would have one column of your matrix zeros. And that, of course, means that the matrix is not invertible. Does it answer your question? Okay, perfect. Okay, can we do something like this? Let me just think about it a little. So, I just want to debug something. This is okay. So this is 1. So why don't we do this? Let's do this. Let's write it sine and sine. For the DC one, this is let's do this. Let's see if it still works. Okay, so it means that just the first component is not the only issue. There are other issues as well. Okay, but I don't know what these are, but just the I equal to 0, j equal to 0 is not the only problem because I fixed it. I give it a constant, but it still doesn't work. Okay, any other questions? Is this clear? This linear regression in DCT basis for 2D data for images. Although I did it for 1D, like I restructured the 2D data into 1D, but still the core idea remains the same. Are there any questions? Do you always have to transform it to 1D? No, you don't have to. You can do it in 2D as well. But then the thing is the products have to be, you have to think a little smartly because the inverse of this matrix would be A transpose A inverse for a tensor would be slightly tricky. It would not be very straightforward. If you transform it into 1D, things become easy to handle. So I would always recommend transforming it to 1D because if it's tensor and you have to take the inverses, it would be along a certain axis. So or A transpose A has to be a square matrix then. So there are some finer things which we have to think about. But if you do it into transform it into 1D, I think then things become quite easy and quite simple. And the thing is, in most cases, you don't even have to reshape them. You can just use view. So it would be a 2D array, but you can view it as a 1D array and do the same thing. Okay. Any other questions from anyone? Okay. So what 1D? Yes. Yeah. It can be 3D, 4D, 5D data point, but you just have to keep track of adjusting it into a 1D form when you are generating these spaces. So imagine that these bases, they can be a 10-dimensional base, but when you want to do the regression, because you are regressing on a 10-dimensional base, just reshape this 10-dimensional base into a column vector and stack it um, in your A matrix. Is it clear to everyone how to do discrete cosine transform for a 2D image? I want to see some yeses in the chat so that I have some confidence that things are clear. If it's not clear, we can go over it again. It's not too tricky. Do you want me to go over it again? Okay, okay. You don't need to wait like till the end. Just tell me like, oh, it's not clear. Could you explain it again? And I will explain it again. So let me just share my whiteboard so that we can see what we have to do. So basically, we have an image, in this case, a 28 by 28 image. And we say that we want to write this image in terms of discrete cosine bases. So what are discrete cosine bases? So the first discrete cosine basis is, so let me write I is the row. So I is row and J is column. Of course, I would be from 1 to 28 and J would also be from 1 to 28. So the first base, the value at each pixel is cosine of pi I. No, sorry. Let's call this U and V because I and J, I'll call it for frequency. So U times 0 times cos of pi V times 0. So let's say you want to find the value at pixel 10, 10. What would you do? You would put U equal to 10 and V equal to 10. It would give you the value at this pixel 10, 10. And you can do it, of course, for each pixel. So this is my base. Base is 0. This is my 0th base. Similarly, I would have another base, which is cos of pi u1 times cos of pi v0. This is, again, if you want to find the value of this base at a particular pixel, let's say 20, 20, you will just put u equal to 20 and v equal to 20. Okay. Similarly, I have more bases. Cos of pi u0 times cos of pi v1 and so on until we get cos of pi u m. M is the number of bases times cos of pi v m. Okay. Now we say that let's multiply this base with w0, this one multiply with w1, this one multiply it with w2, and this one multiply it with wm. Add all these up and try to call this h of x. your hypothesis function. And let's make this h of x as close to y, which is your image, as possible. So it becomes the same linear regression problem, right? Is it clear? Okay. One thing is that these are in 2D, right? So to make it exactly equivalent to our setup, what I do is to make it exactly equivalent to our setup, what I say is that take this image and make it into a vector. So I take the first column, place it here. I take the second column and place it here. I take the third column and place it here, and so on, right? So this become a vector, just like y in our linear regression. I do the same thing with bases. So I say that, okay, I'll do the same thing with bases. This is my A matrix. What do I put in it? Let's call this, let's draw basis 0, 0. So this is basis 0, 0, which is cos of pi u0, cos of pi v0. U and v are pixel location. So I say, okay, let's take this first column and put it here. Let's take the second column, put it here. Let's take the third column, put it here. Let's take the fourth column, put it here. Similarly, I do it for basis underscore m, which is cos of pi um times cos of pi vm. I said take its first column, put it here, take its second column, put it here, take its third column, put it here. And this also become a big. So now I have, and of course, this is basis 0 now, this is basis 1, this is basis 2, and this is basis m, right? So I can multiply it with W0, W1 up till Wm. And this is exactly a linear regression problem, right? So you can say this is equal to this plus some error, E0, E1 till En. And for this, we know the solution. The solution is W star is equal to A transpose A inverse A transpose B. So I have the value of A, right? I just transpose it, multiply it with A, take inverse, and do the rest of the thing. And that's exactly what I did in the code. So I created these bases, right? This is exactly the cosine function. So it's cosine of pi ui, cosine of pi vj. Okay, this is my basis. I reshaped them such that their shape is a size of the image time number of bases. And then I just use the simple solution of the linear regression. Basis dot transpose time basis inverse times basis dot transpose at image time. Is it clear to everyone? Does everyone understand how we do linear regression for high dimensional data? Okay. I want to see some more yeses. Okay. Is there any confusion for anyone? Does anyone want me to repeat something? If there is, please leave me a message. If you don't want to put it in the chat, leave me a direct message and we can go over things again. Can you explain the reshape parameter again? Of course. So basically, so the way I have reshaped, I have shaped my bases. So my basis is 28 times 28 times number of bases times number of bases. Okay, and I want to group these two together and group these two together. In fact, let me write it with a comma, not with product. This is my shape of bases. Okay. So I want these two along the columns and these two along the rows. So I say that let's do bases reshape. And reshape starts by reshaping the last parameter, I think. I think I need to look at the documentation. But what it would do is, it would take this 28 by 28 for I equal to 0 and j equal to 0, put it here. Okay. Then it will take I equal to 1, j equal to 0, put it in the first column. Then I equal to 2, j equal to 0, until you reach I equal to num underscore basis. Then it would make j equal to 1, and again start with I equal to 0, stack it here, and it would repeat it until all of these images are stacked. Does it make sense? Okay. Any other questions? Okay. So it seems like things are clear to people. So what I would suggest is that you guys give it a try to solve this question. I will, of course, upload the solution to the website, Solutions of Tier 4. But I want you guys to give it a try. You still have around 50 minutes, so it's a good time to try it. I am here. If there are any questions, I will be available in the chat. And by the way, I upload these videos on the website. Go through them. If there are any questions, anything which is clear, you can leave a comment on the video. I'm looking at them, I'm following them. Or you can send me an email, or we can discuss it the next day. But comment on the video is probably better, because then we have documentation for it. I can answer it there, I can explain things. So feel free to leave your comments. I'm certain that because we are doing the class in a very discussion type manner, I must be making some mistakes in these lectures. If you find some of these, point them out on the video, and then we can make a discussion and correct them there. Okay. This problem is in the handbook. It should be chapter 5, question number 9.4 or 9.5. This is from the handbook. So try to solve this question. 5.4 in the linear regression chapter. In the exercises, you can find this question. Try to solve it, and in fact, do one step better and try to download an image from the internet, a larger image, maybe a colored image with more than one channel, and try to do it for each individual channel and reproduce it, and then see how the result looks. And of course, you would. If there are any questions, I'm available in the chat and we can discuss them. Okay. If there aren't any questions, I'm going to stop sharing the screen and give you guys some time to solve these questions. Okay, so good luck. If there are any questions, please feel free to ask. Thank you. Guys, can I have your attention for 10 minutes? So we have last 15 minutes. Let's just discuss about the general difficulty level of the course. You can unmute yourself, by the way, now if you want to talk. So because we are almost halfway through, I want to see how easy or difficult it is for you guys to follow along. Is it more difficult than what you were expecting? It's easy, or do you want me to go fast or slow? So just give your general thoughts. Unmute yourself and feel free to talk. Come on, don't be shy, guys. It's okay. It's just an understanding as to how to structure the rest of the class. So anything is fine. Any comment is fine. Don't be shy. Just share your thoughts.
Okay, so 2D regression is a bit hard. It does require a little bit of practice, but try to rewatch the video and try to code it. The best way to learn it is to code it. So if you code it and have a look at it a few times, I think it would become much more clearer. In any case, 2D regression is like not the very important part of the course. If you understand regression in general, that should be enough. This is just to show that regression can be extended to more complex problems. So don't worry too much about it if you didn't get it 100%. My suggestion would be to code it. And if you code it, you will probably get a much better idea of what's going on. Another good thing would be to actually visualize the bases. So one thing that you guys can do, in fact, let's try to do it right now. So what we can do is we can you guys see my screen? Is it shared?
Yes.
Okay, so where was it? So let's look at bases. Okay, so basis is this. So we can probably do something like this. So the first space is just a constant. You can see that this is how it looks. The second base looks like this. You can see it's a cosine along the rows. The third base is this. It's a cosine with double the frequency and so on. So you can probably like look at the 18th base and so on. So you can see that it's you're trying to write this image, the original image, in terms of these bases. And you're trying to find the optimum weights. So this might be a good practice to just visualize these. What else? What other observations are there, if any, for you people? Okay, one thing that I want to point out is that on the course website, on the home page, there is a survey right at the end, course feedback. Okay, so you can at any time fill it. It would ask you about the difficulty of the course, your learning, how is the instruction of the course, how likely you are to enjoy a course like this, and questions like this. So just click on it. If, for example, there is some feedback which you think would help you understand this better, just at any time you can give this feedback. Okay, and don't be shy in feedback. It's anonymous. Nobody, I won't know where it comes from. So you can be critical. You can give your opinions freely. I don't mind. It's just I want your feedback so that we can improve things for the overall instruction of this course. Okay. So with this, if there are no other comments, I will stop sharing the screen. I will be available in the chat for the next 5 minutes, and we will end this lecture around 1. Okay. Thank you, guys.